The background to this guidance note was a request from a client to attempt to explain why tests run on nominally identical test bearings in two different test rigs gave radically different bearing lives. In this case, the bearing in question was a 7206 angular contact ball bearing, and tests were run at nominally identical test loads. Other test parameters were not disclosed. The results showed 2 orders of magnitude variation in fatigue life between the two test setups. We concluded that this must be because of significant differences in test bearing lubrication, giving rise to significant variations in contact morphology. My aim here is not to give a lengthy discourse on rolling contact fatigue, but to give some basic guidance, possible benchmark calculations, and assorted caveats to assist those interested with experimental design. And having covered some of the basics, I'll conclude with a review of different test geometries and how these can be used to best advantage. Rolling contact fatigue involves the initiation and propagation of cracks, which can lead to surface pitting, spalling, and ultimately failure of the bearing surfaces. While load is a primary factor in fatigue life, lubricant, lubrication regime, and material properties all influence rolling contact fatigue. Rolling contact fatigue can occur through both surface and subsurface mechanisms. Surface-initiated rolling contact fatigue, usually referred to as micropitting, is associated with asperity stress interactions, hence rolling contacts of sufficient surface roughness operating under mixed lubrication. Micropitting is influenced by contact pressure, material hardness, surface roughness, and lubricant film thickness. It can occur when lambda ratios, the ratio of film thickness to surface roughness, of less than 5 are generated. Micropitting may occur at between 10 to the 5 and 10 to the 6 fatigue cycles. Subsurface-initiated rolling contact fatigue, otherwise termed macropitting, occurs as a result of high-cycle subsurface stresses generated during rolling motion. Cracks originate beneath the surface of the material, often due to plastic deformation, or at stress raises such as material flaws or inclusions. Subsurface-originated macropitting usually occurs under conditions of fully developed elastohydrodynamic lubrication and at between 10 to the 9 and 10 to the 10 fatigue cycles. Higher applied loads reduce rolling contact fatigue life because of the increased stress amplitudes, giving rise to more rapid fatigue damage and crack initiation and propagation. Because of the difference in the scale of damage caused by macropitting compared with micropitting, it invariably marks the end of component life, whereas micropitting may just result in a reduction in overall bearing life. It will be apparent that, as a rough rule of thumb, tests that end with macropitting typically last about 100 times the number of cycles as tests that produce micropitting. There is, however, one significant caveat to this. Micropitting may act as a precursor and accelerator to early onset macropitting. To quote a recent paper by Wainwright and Kaderich from the Tribology Group at Imperial College London, titled Mapping the Failure Modes of Micropitting versus Macropitting, the key observation here is that macropitting exclusively occurred at higher pressures, 2 gigapascals and 2.5 gigapascals. The lowest test pressure of 1.5 gigapascals never resulted in macro pitting, despite significant micro pitting taking place. This strongly indicates that the risk of micro pitting transitioning to a more critical failure mode of macro pitting is primarily driven by the level of the applied contact pressure, with high pressures making the eventual occurrence of macro pitting inevitable. Idealized test models based on 2, 3, or 4 roller type test geometries are amenable to analysis of Hertz pressure and lubricant film thickness, plus provide no difficulty when it comes to defining and measuring the number of fatigue cycles with or without contact slip. Hence, defining a test in terms of contact pressure and rotational speed, with the result the number of fatigue cycles to failure, is readily achievable. When it comes to rolling element bearings, everything becomes much more difficult, and in the case of axially loaded angular contact bearings, spectacularly so. As a result of this, and going back to the early days of Palmgren and Lundberg, the tendency has been not to define bearing test conditions and resulting bearing life in terms of contact pressure and number of fatigue cycles, but to define the test conditions as applied load on the bearing and rotational speed, with the L10 life simply the number of hours run at that load and speed until failure occurs. So there is something of a difference between how we define test conditions and fatigue life in our idealized and fully deterministic 2, 3, or 4 roller machines and how we do it when it comes to bearings. Radial load is a force acting perpendicular to the axis of rotation. Load is transferred from the inner raceway through the rolling elements to the outer raceway, with force distributed over multiple rolling elements simultaneously. The load, hence the contact pressure on a given ball, depends on its rotational position within the bearing. A rough estimate of the maximum contact pressure experienced by a single ball can be made by assuming that at some point in the cycle the total load is carried by just one ball. This will result in a contact pressure that will exceed that likely to occur in practice. It will be apparent that with multiple rolling elements supporting the load on a radially loaded bearing, that the load on each bearing element, hence the contact pressure, is statically indeterminate. In an axially loaded bearing, it is usually assumed that the load applied to the bearing is shared equally by all the rolling elements and does not vary with rotational position. The assumption of uniform load distribution facilitates meaningful analysis of contact pressure. If a test is to be based on a standard bearing, it makes sense to choose bearings with an even number of rolling elements. For example, a 7209 angular contact ball bearing usually has 12 balls. This means that this bearing can either be used for tests with the full complement of balls or with the number of balls reduced to, say, 6, 4, or 3 evenly spaced balls. In the case of a thrust bearing, such as 51208, the number of balls is typically 13, making it impossible to reduce the number of balls while maintaining uniform distribution. In this case, the simplest solution is to make a modified 12-ball cage, allowing tests to be run with 6, 4, or 3 balls. Let's now consider the motion and contact pressure in an axially loaded angular contact bearing. The first thing to note from this illustration is that the speed of the inner race relative to the balls and the ball separator, not shown, is greater than that of the outer race relative to the separator. It follows that a given point on the inner race will be subjected to a greater number of stress cycles per revolution than the outer race. Now, assuming that the speed of rotation and or the mass of the balls is such that the balls do not generate significant centrifugal force, and that the inner and outer race contact angles are approximately equal, and finally that the balls are in pure rolling, rotating about an axis perpendicular to and in the plane of loading, we could assume that normal loads on each ball are equal and opposite. If we know every detail of the contact geometry, we should be able to estimate the contact pressure on both contacts, noting that although the contact loads may be the same, the resulting contact pressures will be different because of the difference in contact geometry between the inner and outer race. However, although the first assumption may be true at modest speeds, the second and third assumption require further consideration. It should be clear that with an axially loaded angular contact bearing, the static geometry is complicated, but becomes even more complicated with the introduction of rotational motion, deflection through application of load and thermal expansion, all of which change the bearing contact angles, thus changing the contact pressure. As well as the rolling component of velocity, the balls are subject to contact spin, which provides the largest component of rolling resistance, hence the largest contribution to frictional losses and heat generation. If the ball illustrated is running in a straight line on a flat surface, in other words, rotating about the axis R, then contact C will have pure rolling, but points of contact A and B will be subject to contact spin. In this case, failure will occur at either contact A or B before C. Hence, as a test assembly, this will only work as a device for testing rolling contact fatigue in a contact with spin, not pure rolling. If the ball is running around a circular track instead of in a straight line, there will be spin in all three contacts. Spin is defined as rotation within the Hertzian contact. This is what develops traction forces within a pure rolling contact. However, because the traction developed by the spin in all three contacts must be balanced somehow, there is bound also to be slip in each contact. In an angular contact ball bearing, because the ball rolling axis is inclined to the direction of the bearing axis, there must be spin at one or both of these contacts. It is possible for rolling with spin to occur at one race contact and rolling without spin at the other. Except at very high speeds, the tighter curvature of the inner race results in a higher spin moment than at the outer race, resulting in pure rolling at the inner race and rolling with spin at the outer race. This is termed inner race ball control. This illustration shows on the left an idealized contact with the tangents at the ball race contacts and the axis of rotation of the ball all parallel. On the right hand side, the illustration shows what happens if there is, for whatever reason, deflection in the bearing. For simplicity, I've only shown the point of contact moving on the outer race. However, in practice, R inner would increase as R outer decreases. What actually happens will depend on the frictional conditions, lubrication, distribution of loads, both applied, centrifugal and gyroscopic. Moving on to lubrication, rolling element bearings typically operate within a piezo-viscous elastic regime. it will be apparent that lubricant film thickness plays a significant role in determining rolling contact fatigue outcomes. Thicker lubricant films prevent asperity contact and distribute load more evenly across the contact, minimizing stress concentrations that might otherwise initiate fatigue cracks. Thinner lubricant films lead to an increase in asperity contact, leading to increased friction, localized stress concentrations, wear, and potentially micro-pitting. A well-lubricated contact with a sufficient lubricant film generally leads to a longer fatigue life. This might suggest a preference for using higher viscosity lubricants. However, at higher speeds, this may result in increased lubricant shear and the bearing running hot, with the subsequent reduction in lubricant viscosity and hence film thickness. Satisfactory lubrication requires sufficient lubricant to be delivered to the in-running sides of the rolling contacts to ensure that inlets are fully flooded. If this is not possible, the bearing may run starved of lubrication, resulting in premature failure, possibly through seizure. In a rolling element bearing, pressures within the Hertzian contact are sufficient to cause elastic deformation of the rolling elements. The lubricant, providing it has been properly entrained and carried into the contact, is subjected to these high pressures, and this causes a massive increase in its effective viscosity. This is the pressure viscosity effect, and it can cause the lubricant effective viscosity to approach that of glass. The fact that the lubricant is also effectively incompressible means that within the EHD contact, the film thickness is close to being constant. So, under EHD, the solid elements of the bearing are separated by an extremely stiff glass-like film of lubricant. This prevents the surfaces coming into contact and wearing or micro-pitting, but obviously does not prevent the transmission of load across the contact, thus not preventing pressure-generated rolling contact fatigue and eventual macro-pitting failure. It is useful to note that the thickness of the elastohydrodynamic lubricant film is pretty insensitive to applied load, implying that the harder it is squeezed, the stiffer it gets. Assuming that adequate lubrication can be made available in our test rig, it makes sense to make an estimate of the lubricant film thickness, hence the lambda ratio, for the proposed test. This will potentially allow the test to be designed to produce either micro-pitting or macro-pitting. In order to calculate the lubricant film thickness, we use one of the well-established EHD film thickness equations. These are, of course, semi-empirical. A key point to note when calculating the reduced radius of the contact is that the values for the outer race will be negative because they are concave, not convex. Whereas establishing the radius of curvature of the ball is not particularly difficult, estimating the radii of curvature of the outer race track can be more demanding. When it comes to determining the effective elastic modulus, E prime, for an EHD contact, there is one significant potential cause of confusion, and that is the difference between E star, the contact modulus, and E prime, the effective elastic modulus. In calculating contact pressure using the Hertzian contact equations, we use E star, whereas in the various EHD equations we use E prime. The film thickness equation based on dimensional analysis is shown here. Note that the entrainment velocity is the entrainment velocity between the ball and the outer race, which in effect means that the entrainment velocity is half the surface speed of the ball. Numerous different values for the different constants have been proposed, including those from Hamrock and Dowson, Westlake and Cameron, Ranger and Cameron, Ford and Cameron, no doubt numerous others. Regardless of the equation we decide to use, there is one significant caveat, and that is that the pressure viscosity coefficient alpha, as defined, is assumed to remain constant regardless of the shear rate or temperature. In practice, this can only apply to Newtonian fluids at ambient temperature. However, we can console ourselves with the thought that we only wish to estimate the film thickness for the purposes of our experiment. Numerous online calculators are available. Alternatively, you can make your own, as I have done here. If you're not particularly familiar with EHD film thickness calculations, I strongly recommend Jim Greenwood's paper from 2020. Yep, that's the same Jim Greenwood of Greenwood-Williamson fame. This figure shows the velocity profile of a lubricant approaching an elastohydrodynamic rolling contact of the type generated in a two-roller machine. The fluid in contact with the moving surfaces necessarily travels with the surface velocity u. Considerations of continuity suggest successive velocity profiles as the fluid approaches the contact of the form shown in the sketch. The film thickness h in an elastohydrodynamic contact is largely determined by processes taking place in the approach or inlet zone to the contact zone proper. In this region, lubricant entering the contact has been subjected to intense shear if at only moderate pressures. Then, on its passage into the contact, further shear at a lower rate but increasing pressure. If the response of the lubricant to this combination of shear and pressure is non-Newtonian, that is, if shear stress ceases to be proportional to shear rate, it may be expected that its behaviour in the approach region will differ from that of a Newtonian fluid of the same nominal characteristics. It is this act of shearing that gives rise to loss of apparent viscosity in polymer thickened oils and limits the usefulness of viscosity index improvers. It is perhaps no surprise that we have a lubricant shear stability test, the KRL test, which involves running a loaded taper roller bearing under load immersed in a small volume of test oil for a number of hours. This is followed by measurement of the kinematic viscosity of the lubricant. The specified test durations are 4 hours, giving 348,000 revolutions, 8 hours, giving 696,000 revolutions, or 20 hours, giving 1,740,000 revolutions. In other words, in an immersed test with just a small volume of lubricant, said lubricant is degraded long before we achieve the number of cycles necessary to produce macro pitting. Bearing in mind the influence of lubricants on rolling contact fatigue behaviour, plus the influence of shear and temperature on lubricant performance and life, it follows that a bearing test designed to evaluate the performance of a material will ideally be run with minimal change in lubricant properties, and a bearing test designed to evaluate lubricant properties will ideally be run in such a way as to maximize the change in the lubricant properties in the shortest possible time. It follows that for a test of the material properties or bearing design, lubricant should be circulated through the test assembly from a large volume source, which includes filtering, such that changes to the overall lubricant properties are limited to those associated with temperature viscosity effects within the test assembly, and not other properties associated with exposing the lubricant to temperature and mechanical shear. Bearing tests to evaluate lubricant performance invariably involve subjecting a specified small body of lubricant to both temperature and mechanical shear to promote lubricant degradation and explore its resulting effects on material or bearing performance. Note that for higher frictional loss bearing types such as taper roller bearings, it may be necessary to include cooling passages in the test assembly. Here is a simple illustration emphasizing the difference between a material test with circulating lubricant and a lubricant test. Lubricant flow also provides a principal means of removing heat from the test bearings and associated test assembly. The following graphs show the effects of varying the test speed on an axially loaded 7209 bearing under constant load and varying the load at constant speed. In both cases, increase of speed at constant load and increase of load at constant speed both lead, as one might have predicted, to an increase in bearing temperature, hence reduction in lubricant viscosity and elastohydrodynamic film thickness. In both cases, the test bearing ceased shortly after the bearing temperature exceeded 120 centigrade. In other words, another form of bearing failure was precipitated, but this was neither micro nor macro pitting. A corollary to this observation is that with a controlled lubricant supply, it may be possible to achieve a lower stable bearing test temperature with a higher lubricant inlet temperature, hence a lower lubricant inlet viscosity, and at a lower flow rate, hence lower churning losses, than with a lower inlet temperature and/or a higher flow rate. This is an analogous problem to that created when overfilling a grease-lubricated bearing. The optimum fill is typically about 25% of the bearing free space, and overfilling the bearing with grease will often cause it to fail prematurely. Of course, instead of using calculations, we could actually attempt to measure the lubricant film thickness. Optical film thickness measurement provides an attractive and informative method. The measurement involves loading a steel ball against a glass disc with a semi-reflexive coating. However, the method suffers from one serious limitation: the strength of the coated glass. Because of this, contact pressures cannot exceed about 0.8 gigapascals, and in order to preserve the coating are typically limited to about 0.5 gigapascals. There is a significant caveat arising from this. It takes something of an act of faith to assume that the lubricant tested in an optical elastohydrodynamic film thickness measuring device at 0.5 GPa is going to behave in the same way as at a contact pressure of, say, 2.5 gigapascals in a contact between a bearing steel ball and a bearing steel race. There is not much we can do about this problem. Whereas optical film thickness measurement produces an accurate representation of the lubricant film thickness profile in the contact, all other methods result in only an average film thickness for the contact as a whole. Two capacitance film thickness measurement methods are available, one in which the space between the two surfaces is treated as a capacitor, and the other in which a fully isolated capacitance probe is inserted into one surface to measure the gap between the sensor and the counter surface. The first method can potentially be used in systems where both surfaces are moving, for example in a two-roller type contact. The second method requires the surface carrying the capacitance probe to be stationary, hence, for example, the outer race of a bearing. A small hole is drilled in the bearing race and the probe is inserted flush with the race surface. As a rolling element passes the probe, a change of capacitance, which is a function of the lubricant film thickness, can be detected. This is, of course, a transient measurement. Both methods require knowledge of the dielectric properties of the oil, and both are limited to producing only an average film thickness measurement. Ultrasonic sensors can be fitted to a stationary component in a rolling element bearing, typically the bearing outer race. Unlike the capacitance probe, there is no requirement to drill a hole in the bearing race. Ultrasound measurements utilize the fact that sound waves are reflected from different surface interfaces, hence at the boundary between the bearing inner race and the lubricant, and between the lubricant and the surface of the rolling element. Reflection, resonance and phase-based methods can be used to determine the lubricant film thickness. Although this is a viable measurement technique for systems in which a steady-state lubricant film occurs, for example a plain journal bearing, we have some doubts with regard to how practical such measurements are when measuring transient film thicknesses, as must occur when a rolling element passes a point adjacent to the sensor. If we have two surfaces separated by a thick non-conducting lubricant film, we effectively have an open circuit switch, so nominally an infinite resistance. A contact resistance signal will thus be the open circuit voltage of the system. If the fluid is a mineral oil, it will have very high electrical resistance. Oils are good insulators. If the surfaces are brought together but remain out of contact at an asperity level, the switch will still be open circuit, so the contact resistance signal will still be high. In effect, once there is no metal-metal contact in the switch, it does not make any difference whether the surfaces are separated by 100 microns, 100 millimeters, or 100 meters. As the surfaces are brought together, perhaps through a reduction in entrainment velocity or lubricant inlet viscosity, electrical contact is made through the film, initially at an asperity level, at which point the switch is momentarily closed, producing a short circuit between the surfaces. As a result of this, the voltage across the contact falls to zero while the asperities remain in contact. It will be obvious that each asperity is in effect an individual switch, so just one asperity coming into contact will be sufficient to produce a short circuit. However, we may have many more than one asperity in contact. In other words, we have multiple switches in parallel. There is no way of telling from the contact resistance measurement how many closed switches there are. It could be 1, it could be 100. So whereas the contact resistance signal cannot be used for determining lubricant film thickness or the number of asperity contacts, it can be used for indicating whether there are or are not any asperity contacts, hence whether the contact is running with full elastohydrodynamic separation or under a mixed lubrication regime. In order to generate elastohydrodynamic separation of the surfaces, any system must fulfill three requirements. Firstly, a lubricant with sufficient viscosity and pressure viscosity coefficient is required. Secondly, there must be a mechanism for delivering the lubricant to where it is required and in sufficient quantity to flood the inlet to the contact. Thirdly, there must be a sufficient entrainment velocity to carry the lubricant into the contact in order for it to generate the necessary elastohydrodynamic separation. The first sketch illustrates what happens in an elastohydrodynamic contact between the surfaces running with the same surface velocity with a fully flooded inlet and a lubricant of sufficient viscosity. As mentioned previously, the system is weakly dependent on load, so that once an elastohydrodynamic film of sufficient thickness to separate the surfaces is generated, increasing the load has little impact on the level of separation. This is what happens if there is insufficient lubricant to flood the inlet, starved lubrication, or the lubricant inlet viscosity is too low, which can of course be caused by having a too high lubricant inlet temperature. In this case, we cannot prevent intimate contact between the mating surfaces at an asperity level, so we may end up with seizure or micropitting depending on the test conditions. Frictional torque in a correctly lubricated rolling element bearing starts more or less at 0, then increases with increasing speed of rotation. Rolling element bearings are, by definition, very low friction devices, and measurement of frictional torque is not of very general interest. It only becomes of interest in more specialist circumstances, usually associated with operating bearings at very high speeds. In this case, the increase in frictional torque may be caused by churning or shearing of the lubricant, sliding contact between the rolling elements and the cage, skidding in lightly loaded bearings, etc., all of which cause the bearing to heat up and possibly fail. Measuring the frictional torque in the bearing may be useful if one wishes to calculate the power losses associated with a given bearing. Otherwise, measuring the bearing outer race temperature is a useful and less complicated way of determining if something is going wrong. Higher loads lead to a shorter time before crack initiation and propagation, thus reducing the bearing's fatigue life. The graph has been generated using the SKF online bearing life calculator for an axially loaded 7206 angular contact bearing running at 6,000 RPM and a temperature of 70 centigrade. The key thing to note from this is that increasing the load from 5 kilonewtons to 10 kilonewtons reduces the L10 life from 1,360 hours to 170 hours, in other words, by a factor of 8. Increasing the load from 10 kilonewtons to 15 kilonewtons reduces the L10 life to 51 hours, in other words, by a factor of 3.3. Bearing in mind the risk of precipitating other failure mechanisms through applying excessive load, reference to this curve provides some guidance with regard to choosing the optimum test conditions for rolling contact fatigue tests. Not too long and not too short. Now, let's consider the importance of running in. In rolling contacts and rolling element bearings, shakedown refers to the initial running in stage where, providing the contact pressure is not too high, microplastic deformation and work hardening occurs. This leads to a build-up of residual stress and a subsequent increase in the contact's ability to withstand cyclic loads. After this shakedown stage, the bearing material can behave elastically under loads above those associated with the initial pre-shakedown elastic limit. The material has become harder and stronger. Residual stresses are stresses that remain in the material even when the external load is removed. After shakedown, the load experienced by the material is subjected to both contact stresses and the residual stresses introduced during the shakedown process. At this point, further elastic deformation ceases to be possible, and the material achieves a steady-state running condition, which is a necessary precondition for any subsequent rolling contact fatigue test. This running-in process is referred to as elastic shakedown. The elastic shakedown limit represents the highest stress that can be applied to the contact without inducing macroscopic plastic deformation. The steady-state running condition can only be achieved if the stress induced from loading is below the elastic shakedown limit. If the load during initial running in exceeds the elastic shakedown limit, each load cycle will result in a combination of elastic and plastic deformation in a process termed plastic shakedown. If the load remains below the plastic shakedown limit, in due course the material response becomes one of steady-state cyclic plasticity. Increasing the load during running in still further results in progressive plastic ratcheting of the surface, leading to premature failure. Steady-state conditions can never be achieved. In a bearing, elastic shakedown typically takes between 10 to the 4 and 10 to the 5 cycles, and the elastic shakedown limit is typically considered to be around 2 gigapascals. The elastic behavior of materials under rolling contact is crucial to predicting the fatigue life of components. It follows that after satisfactory running in, subsequent rolling contact fatigue tests should be carried out under primarily elastic contact conditions. Detecting macro pitting is easy using a simple vibration sensor or a microphone buzzer. This is because when macro pitting occurs, it results in a large amount of noise and machine vibration. Detecting micro pitting is a much more challenging proposition, as the levels of surface damage are typically too small to induce significant mechanical vibration. Indeed, damage may be limited to nothing more than the visible dulling or greying of the surface. In this case, optical examination is the primary method of establishing if micro-pitting has occurred. However, this clearly requires the test surfaces to be accessible for observation. Another yet unproven method of detection that does not require direct observation of the surfaces is to use low ohmic value electrical contact resistance measurement to detect changes in conductivity of the contact. The assumption here is that the presence of micropits may increase retention of oil on the bearing surface, resulting in a small change in conductivity. For determining failure by macropitting, we need nothing more than an uncalibrated output from a basic vibration sensor or microphone. The output can be time-smoothed and damped. The magnitude of the signal is meaningless, and it is only used as a trigger or alarm device, not for making any analytical measurement. If we want to measure vibration in a meaningful way, we must use a properly calibrated accelerometer with high-speed data acquisition of the dynamic signal. Having acquired the signal, for it to be of any use at all, we need to process and analyze the output in order to convert the raw data into meaningful content. Frequency analysis is the most commonly used method for analyzing a vibration signal. The most basic type of frequency analysis is a fast Fourier transform, which converts a signal from the time domain into the frequency domain, allowing a power spectrum to be generated, showing the energy content in specific frequencies of the overall signal. This is useful for analyzing stationary signals whose frequency components do not change over time. It is not suitable for signals whose frequencies vary over time. If we have something like a bearing rotating at a given speed, it will generate a signature frequency or frequencies. We might sensibly decide to focus on these specific frequencies for monitoring and analysis purposes. Order analysis is used to analyze systems where the excitation frequency varies, for example, changes in running speed of motor. So it is geared specifically towards the analysis of rotating machinery and how vibration levels and frequencies change as the rotational speed of the machine changes. Wavelet analysis is used for characterizing machine vibration signatures with narrow bandwidth frequencies. In essence, we pick up a given frequency that we wish to monitor and use that as our measured parameter. This is a bit like saying, I'm not interested in the overall volume of the music. I am only interested in monitoring the volume of noise at middle C. 256 Hz if you're a mathematician and 261 Hz if you're a musician. Then there are more complicated forms of analysis such as models-based analysis. Hence we really need to decide what it is we want or think we need to measure when it comes to vibration measurement and analysis. Then choose an appropriate bandwidth sensor, then choose an appropriate analysis system. It is not enough just to data log some parameter. We really need to know what the signal means and how it is to be interpreted. Now let's revert to considering different rolling test configurations. Having rehearsed many issues, we can now summarize how to use the many different test geometries available for investigating rolling contact fatigue and other aspects of bearing life. Here are some of the things we may wish to investigate: bearing rating life, friction and power losses, bearing temperature limits, bearing churning losses at high speed, lubricant and grease performance, rolling contact life of candidate materials. Pure rolling test geometries can be divided into three basic categories. These tests use standard rolling element bearings as the test component and can be used for bearing rating life tests, measuring bearing frictional, hence power losses, determining the temperature limits for the bearing, evaluating the performance of a lubricant or grease, measuring churning losses at high speeds. These tests are aimed at stressing a single rolling element component, either a ball or a rod. These tests are used for investigating rolling contact fatigue life of different candidate materials, effects of surface finish and coatings, performance of lubricants and greases in idealized contacts. Hybrid test geometries use the rolling elements and one raceway from standard rolling element bearings, with the other raceway replaced with a simplified and easy to manufacture specimen of candidate material in the form of a disc or cone. These hybrid test geometries are primarily designed for evaluating rolling contact fatigue life of candidate materials. So, to conclude, before we start, we need to decide whether we need a bearing test, a materials test, or a lubricant test. We then need to choose an appropriate test geometry and test conditions, paying particular attention to the lubrication regime under which our tests are going to be run, hence to achieve the required failure mechanism. Our test must include appropriate running-in procedures at contact pressures that will achieve satisfactory elastic shakedown. Subsequent test conditions must be at contact pressures consistent with the production of the required failure mechanism. This will rarely exceed a nominal contact pressure of approximately 2.5 gigapascals. If you would like to discuss any of the issues I've raised in this presentation, please contact me direct at info@phoenixtribology.com.